well, guess we'll just talk. How many people are natural gas engineering majors? 1, 2, 3.
Unofficially.
Unofficially. And what are the rest of you?
Petroleum.
Pardon?
Petroleum. PE.
PE. So you're getting your master's in PE. How many people are getting their master's in PE? Oh, quite a few of you. Okay, how many chemies do I have in here? 3. Okay. And so let's start over here. Why are you taking this course?
Just elective course, so I want to like.
So why did you, okay, I understand it's an elective course because you're not a PE major. Why did you select this course as an elective?
Okay, personal interest. Personal interest. So my previous master degree is in natural gas hydrate. So that's why I'm very interested in natural gas.
Okay,
thing.
okay.
Well, my master's is in natural gas engineering, so I want to know more about it.
I thought you're not a chemi?
Yeah, like my bachelor's is in chemical.
Oh, no, I'm
engineering.
sorry. What I was looking for is people not that have a degree in chemi, but that are working on their graduate degree in chemical engineering that are taking this as an elective.
Oh, okay.
There's nobody in that category. I usually get a couple of those. You are?
Yeah.
Okay, yeah, okay. So we have one chemi major,
Okay.
I'm a chem major.
and you're a chemi major. And then why are you taking this as an elective?
Just to learn more about it. I have already accepted a job and just
With?
to kind of, as
With?
a process engineer with Holly Frontier,
Okay.
and it's oil and gas, so just kind of
All
learn
right,
more
so
about
you're
that side.
trying to get into some oil and gas. All right.
Mhm.
Because I can talk about a lot of things in here. Normally, I'm basically a reservoir engineer, so I will gear things toward that rather than, let's say, processing.
Mhm.
And you guys are PEs, so you're still taking this as an elective because this isn't a required course. So you heard that I was an easy teacher, or why are you taking this course?
Actually, I had another course that is statistical modeling. I attended the class yesterday, but I am not interested. So I'm trying to replace that subject with this. So today I just sit over here to decide
Okay,
later on.
good answer. Okay, now does everybody have the syllabus up in front of them? Okay, so, well, I can pull it up at the same time. We can look at something together. And I think if we can look at stuff together, I think we'll be all right. Oh, you know what I can do is I can move some stuff into D2L and we can look at it together too. We'll get this done. Where am I? 5613 syllabus. Okay. So we're going to have a test on September 18th. That's all you really need to know, right? And I'm really only going to cover 3 chapters in this book. I used to try to cover 4 chapters. I used to do flow in the well bores. So a well bore or gas flow from reservoir formation to the surface. But I'm just going to do basic properties of natural gas in chapter 1, and then chapter 6 and 9 are both really dynamic. One has to do with how we determine well, they both have to do with how we determine reservoir characteristics. One is a field called transient pressure analysis, and typically what we do with a producing well is we shut it in or measure the drawdown with a pressure gauge and try to keep a constant rate, which is real easy if you shut in the well, because that is a constant rate of 0. And then we measure the So this is very similar to putting a thermometer into a pot of water and turning the stove on. The heat's going to go up, right? But the heat will go up faster if I put the temperature gauge on high, or the setting on high instead of low. And so by measuring the rate of change of temperature, I'm actually measuring the heat capacity of the stovetop. So we can't really see petroleum reservoirs, and so we measure things at the surface to try to get an idea of their size and their capacity to flow. And we do that by measuring the pressure, and sometimes we just measure the rate. In an ideal situation, we try to get as much production out of a well as possible, so we try to produce it at capacity. And typically a gas well flows into a pipeline, and a pipeline has a constant pressure. So when we flow a well into a constant pressure pipeline, then the production rate can be measured, and it can tell us these same types of reservoir characterizations or characteristics. Any questions on that? So we're just going to do 3 chapters. I'm going to cut off the chapter that I usually run. And I used to assign homework, but then it became time-consuming to grade homework. So we're just going to work some problems in class. And we will actually work a problem in class, even though we don't have any technical support here. This is mad. I can't even get this touchscreen that was working at the beginning of the hour to come on. It's a pretty short resume. I come in early on Monday, Wednesday, or Tuesday, Wednesday, and Thursday. But for the PE and natural gas engineering majors or anybody that's on campus, you can drop by my office anytime you want to. If I'm there, you're welcome to see me. You don't have to see me during office hours. I just try to post when I know I'm going to be there. And also, if you want to see me, you can always just email me and make an appointment. So how many people are planning on getting the text or have ordered the text? Okay, the text I highly recommend. If you're going to have any kind of career in petroleum engineering or natural gas engineering, this is a very thorough textbook. And even though I don't cover all the chapters, once you get to know how to use 3 of these 12 chapters, the other chapters will be very useful when you have those types of specific problems. Okay, let's see if I can't just hang some stuff in D2L so you guys can follow along. I think let's see, what am I here? So that's 5613, PowerPoint's 2013. I was just going to show these. D2L. Content, and a module. Do you guys have two files in content now? One called production systems, one called phase envelopes? Yeah. Yes?
No,
Yeah, one six.
mine sold us.
Maybe I have to hit done. Okay, now maybe.
Yeah.
Yes.
Okay. Let's just open up production system. It's just, I think it's just, well, it's 2 slides. We're looking at production systems, right? Um, So if you're not real familiar with this stuff here, you have to memorize everything here. How many people have an undergraduate degree in petroleum engineering besides Gene? Okay, you have undergraduate degrees in petroleum engineering? Well, there's nothing new on this slide to you then, is there? Okay, so people from chemical engineering, they need to familiarize with this kind of stuff. We'll kind of get a merge here. So there isn't a whole lot of stuff here. What we have there is a picture of a reservoir at a subsurface at the bottom of figure 1.6. Is everybody with me?
Yeah.
And it's basically showing some laminated formations, and kind of the charcoal gray in the middle there with the letters on it is showing a producing formation. And every producing formation, in order to get it produced, you have to draw down the pressure. So when you open up the wellbore, although there's going to be some pressure as you translate from the surface to the bottom hole conditions, you're basically, it's like shaking up a can of Coke and then taking off the top, because you have more pressure in the bottle or can of Coke than you had in the atmospheric, so it flows. And the 3 lettered symbols there are PWF, which stands for the pressure of the well flowing, and there's a PE, which is the external pressure, and in any reservoir, there's a theoretical average reservoir pressure, which is defined as the pressure that would be obtained if you had been producing this reservoir and shut it in for an infinite amount of time. It would stabilize from the internal to the external to some average reservoir pressure. And the next slide kind of shows that drawdown from flowing pressure to external pressure. Then you work your way up the wellbore, and you come to what you would typically see for a wellhead for a gas well. Now, for an oil well, you might see a pumping unit, but for a gas well, gas wells typically flow on their own. And so it usually just goes to a separator, and if the gas contains some liquids, either oil or water, they'd have to be separated out at some, so they're showing 2 vessels at the surface. Okay, are there any questions on that slide? So let's close that PowerPoint and open the one that's called phase envelopes. I still haven't figured out exactly how to Okay. Oh, did yours say 5990?
Yes.
That's all right. Okay, let's go to slide 2. Slide 2 is like water. There's no phase envelope. if you have a single component system like water, you have a critical temperature and pressure above which you cannot differentiate in what they're doing with that grayscale showing the density. So at atmospheric pressure, water boils at, and this isn't water, but the idea is that it's a single phase or single component system. Whereas what we have in hydrocarbons is always a multi-component system. I don't know of any oil or gas well that doesn't have methane in it, or ethane, or propane. It's just that how these molecules are arranged and in what combination and percent of they are will determine what kind of phase envelope we have. So let's go to the next slide. And it just says, I think there's an animation. Let's just go ahead and run the animation. So 2 clicks until you get the GOR, the color density, composition, reservoir pressure, and temperature scripting at the bottom. And then I'll just kind of draw this. So above the critical, the cricondent term, you're always going to be single phase gas. Okay, so I'm kind of try to outline what's in this course and what's not in this course with these phase envelopes. So obviously, anything in a phase envelope that is gas is out here. Okay, now unfortunately this PowerPoint starts with oil, so I'm going to move on to the volatile oil reservoir. And so initially it's here, and I'm going to look at the path of reservoir depletion. It doesn't change temperature, so it just comes straight down. And what this phase envelope is depicting is quality lines for percent gas and percent liquid. So this is 100% liquid up to some critical point, not the cricondent term, and this is 100% gas. So this could be, if we're going with liquid, this would be 90% liquid. Anytime you're in the phase envelope, what 2 phases do you have?
Oil and gas.
Okay, or liquid and gas. Okay, oil and gas, yes. So anything to the right in the reservoir and at the surface is going to be gas. Anything that's in the phase envelope is going to be both. So it's kind of included in this course because it's gas. Okay, I am on, I want to jump to probably the most typical situation for gas engineers. I think I'm on slide 7 of 9. Yes.
What's the name of that slide?
Pardon?
What's the name of the slide?
Wet gas reservoir.
Thank you.
Okay, so here is for this composition and for this phase envelope and for this initial pressure and temperature, this is what's important. In the reservoir, and this is what we're going to talk about most of the time, its path of depletion is above the cricondent term, which means in the reservoir, it never enters, it stays in a gaseous phase the whole time. It's single phase. But because we have a decrease in temperature as we bring it from reservoir temperature to maybe 200, 250, 300 degrees. As we bring it to the surface through its path of depletion, this is, remember from the first slide, this is up the wellbore. As you go up the wellbore, you decline in pressure and you decline in temperature. Then when you get to the surface, even though this came from a reservoir that is single-phase gas, when it gets to the surface, it's two fluids. Okay? Now, in chapter 1, I'm going to draw our other slide up here. We got a wellbore. Of course, the slide in the book's a little bit better. We got a reservoir, and at the surface we have maybe one or two vessels after we go through a wellhead. And from this, they have oil and gas. I'm just going to put it liquid, and then we have gas. Okay, so we have some fluid contact in here, and the way a separator works is usually there's a liquid dump. Okay, so you slow the fluid down, put it in a vessel. It develops a gas-liquid interface, and it says if that liquid phase gets too high in there toward the outlet to the gas, they don't want to send any liquid up to that gas thing. So as that level rises in that separator, a controller dumps the liquid out and raises it back down. Okay, so let's look at what gets measured normally in the industry and what kind of corrections we have. We sell this gas, okay, to the pipeline. And there's an important term that we use called custody transfer. If I'm Devin up here in Oklahoma City and I drill this well and I am now put in my wellbore and my separator, and at this point, right here, there's probably some kind of meter, and someone like One Oak, who's a midstream operator in Oklahoma, they're going to buy the gas. When they buy the gas, they don't want to know what it is. This is kind of a long story, but I'm going to try to come back to this. So what they do is they take a sample of the gas. Depending upon the value of the gas, they may do this daily, weekly, or monthly, and how much gas is flowing. And what they do is they'll run an analysis on it. And you can see in your textbook that there's several example problems where they show the analysis of a composition of a typical fluid. Let me see what the first one is. That's all the properties of them. Okay, on page 4, table 1.2, composition of a sweet natural gas, example 1.1. So it shows, starting with nitrogen, methane, methane, and propane, what a typical composition is. Now, the gas gatherer is what they're usually referred to as by the producer, the person that gathers their gas. Samples this, and they're going to pay us money. And if you just read the Wall Street Journal, you would think there's only one price for all gas, right? It's like $3.84 an MCF, right? It's been under $4 the last 4 or 5 months. It creeped over $4 about a year and a half ago. It was down under $2. Everybody following me? You'd think there's just one price for gas, okay? But that's not exactly true. That's an average price, okay? So who can tell me what would affect the price of the gas?
Supply and demand.
Transportation fees.
Question. BTU value.
This is what I was looking for. All those other answers were right. Sometimes when I ask a question, it gets kind of dangerous. Okay, so the BTU, and why is that important?
Tells you how much energy you get out of it.
That's how much energy you get out of it. This is good. There's another even bigger answer than this, but the more methane it has, in some gases, almost 100% methane. I looked at deep Anadarko wells, they're like 99% methane, so they actually have a BTU content less than 1,000. And so a gatherer, again, is going to look at the value of the heating content as an indicator of how much they're going to pay the producer for the gas. So if there's only about 70% methane and let's say 30% propane, it's going to have a lot higher heating content and it's going to be of more value. Okay, staying on that bent, what else? Why else would they pay you more for your gas? Sweeter gas. Less and
Quality.
okay. Actually, that if I ask the question, why would they pay you less for your gas? You could allude to impurities. Hydrogen sulfide would definitely be something that if you have some gas in Wyoming has like 20% hydrogen sulfide, but the wells produce like 10 million cubic feet a day, so it's worthwhile to do something with it. Now, typically a contract will say something like, I will only take your gas if it only has this much water and this much impurities. And then we can handle a little bit of impurities in our pipeline. And when we get to our refinery plant, we'll take the rest of those off. But they're not going to pick up gas that has 20% H2S. They're going to tell the operator they have to build their own scrubber at the well site and knock out and get that down to a tolerable level. Because the midstream player has to transport it a ways before they can even start to clean it up. So there's probably some minimums for contaminants that they're going to put on from the wellhead. And actually, most gas in the country that's produced is capable of being picked up by the transportation company immediately. In other words, it won't damage the pipeline. It isn't so corrosive with CO2 or hydrogen sulfide that it corrodes the pipeline. So it's usually a safe bet. Okay, so we know that there's some things that will cause the gas price to go down, and there's some things that will increase the gas price, the heating content. And you see in your textbook, does the table have the heating content? See, okay, it doesn't. And I remember that. And normally, I think in Dr. Sharma's course that you use the
PSA?
yes.
We covered it last night.
You've already had the course?
Well, he had the class last night. He already talked about it.
Okay, so you got the big notebooks. Are those required for that course?
Not required, but recommended.
Okay, and I have them, and I have one handout that I'll hang up here, but in addition to the critical properties of the gas that you have in this textbook, it has the heating content for each of the gases, so they can figure that out. And so they'll just take the sample, and they don't actually do lab experiments. All they have to do is get the analysis, and then they just use normal mixing rules. They just column multiplication and row addition. You know, the heating value with this percent of the different gases. Okay, one more thing that's important.
You're talking about if they can get liquids out of it?
Liquids. Okay, and this became a bigger and bigger issue when the price of oil and gas really separated. Now, who can tell me an approximate number for the BTU value ratio of a barrel of an oil to an MCF of gas, 1,000 standard cubic feet?
171?
Huh?
171?
No.
1 to 6.
1 to 6.
So it depends upon the composition.
It depends upon the composition.
Yes.
The gas can
Right.
change the composition and the oil can change the
It's subjected
composition.
to
Yeah.
temperature.
6 is a number that we
Yeah.
loosely use.
5.9 or 6.
Yeah. So, if all we ever did with oil and gas is burn it, you'd never pay more than 6 times for oil than you would for gas. So, at $4 an MCF, the most I'd pay for oil is $24. But oil is $100. Okay? Now, there's some reasons for that. Oil can be transported. So, and it's denser. So why is that valuable? Well, our cars run on gasoline or diesel, even though there's a push for compressed natural gas vehicles, and we've had vehicles that run on propane for decades. And I think there's a town, and I think one of the major cities in India has been running on compressed natural gas for 30 years, and that wasn't to do with the liquid gas price differential, but it has to do with air pollution. And that's why there's more compressed natural gas stations in California than any other state in the United States, is they're concerned about air pollution, and natural gas runs cleaner. So there's other issues there. But back to why natural gas can have a higher, why sales gas can have a higher price is if there's liquids that are entrained in it, so that based on its composition, they can figure out when it gets to the refinery that they're going to be able to get liquids. Liquids are always, or currently, I say always, probably always, are going to sell them for more, or have more higher market value than gas. Even though the BTU has already been taken care of, there's still an additional value just because the BTU is in a liquid form. And right now that's at a huge premium worldwide. Liquid's more valuable than gas. Transportation. It's really hard to get that gas it's expensive to compress gas either to liquefied form and then keep it chilled on tankers, and all that's required. $1 billion investments for ports to handle these things.
Excuse me.
Yes.
Like you said, the gas price actually depends upon the BTU, the impurities, and the liquids. And what I know is, in the Canada and other part of the world, the gas price is linked with the oil price. So what's the logic behind why they are linking the gas price with the oil price?
This is a very good question. When I actually first heard that the reason that in Japan gas is as high as $12 or $16 because it's linked to the oil price, they're trying to put it. There's no valid reason. I mean, my short answer, even though it sounds silly, is it's political. Okay. Because if they want gas, it's really what they're willing to pay for the gas. It's really supply and demand. Now, that the seller is saying that I'm going to say it's this much because it's this fraction of the oil price is somewhat arbitrary. There's no market reason. So in our country there's a complete disconnect. Oil and gas prices can move anywhere they want to. There's no connection between the two. Now, some things happen in our industry, and let's bring coal into this mix, right? Because a lot of this has to do with electric generation. For a long time, more of our electricity was generated by coal than by natural gas. And we just, because natural gas prices are lower, we're crossing that. And right now, more electricity is being generated by natural gas. And then we can look at heating. Okay, so when I grew up, we had heating oil, number 6 heating oil. truck would come by and put oil in there, and then we had a furnace, and it heated hot water, and then circulated through our home, so. But this was in the north, and they need more heat than they do in Oklahoma, which is not that cold in the winter. So the idea is that there's many aspects of consumer and industrial use where if the price of this goes up, well, I'll just use this. If the price of that goes up, I'll just use this. And really the best example is coal and natural gas for the generation of electricity. Large conglomerates that generate electricity have 20 coal-fired power plants and 20 natural gas-fired power plants. And they can, depending upon the price of the commodities, they can change those. But you, in your car, knowing that you can buy compressed natural gas for $1.12 doesn't help you, because your car is not equipped with a lever that lets you run on compressed natural gas rather than liquid fuel. So most of us are trapped, okay? My house here in Norman, Oklahoma, if something happened to the natural gas supply that runs my heat in the winter, I don't have a choice. Or if natural gas prices just skyrocketed, I don't have a choice. I don't have a heater that will run on number 6 fuel oil as an option. So most end use is dedicated, and so politically we try to maybe make some changes. T. Boone Pickens is trying to get 18-wheelers to run on compressed natural gas, and I kind of agree with some of the things. People, you should all realize that we have a natural gas glut in the United States, okay? There's countries in the world that are crying for natural gas. All of Europe needs natural gas. Most of Asia needs natural gas. And there's some countries like Australia and Qatar that have an abundance of natural gas that have to ship it to those places. But the United States has moved from a net importer to a net exporter of natural gas. We have a glut of natural gas. Our gas price is depressed. But that doesn't mean you won't be able to find work. There's going to be some changes that are going to happen in your careers.
Excuse me.
Hmm?
Is that related to unconventional gas? Is it?
One of the reasons we have a glut of natural gas is the largest increase in production has been from unconventional resources. And it's not just unconventional resources. It really has to do with horizontal drilling
Technology.
and multi-stage fracking, because we're increasing our production from oil wells, shale wells, gas wells, shale oil wells, heavy tar sands. We're increasing the production of anything that we ever produced before because of horizontal drilling and multi-stage fracking. So the United States and several other countries, because of this technology, has changed from declining production to increasing production.
I read a survey that the United States will be the largest gas producing country in the world, and it will cross Saudi Arabia production in coming 10 years probably.
That's no
You-
gas, natural gas.
There's a oil you couldn't.
We're not using a lot, so we're not exporting.
I don't have a crystal ball to predict what's going to happen, but I can tell you there's going to be some changes. Because it doesn't appear that there's any reason why Brazil or Mexico or China shouldn't be able to develop their gas shale potential. But that technology doesn't seem to spread as easy as shipping a tanker of oil or even liquefying natural gas. The technology isn't just in a book or some manuscripts. The way I think about technology is it's also embedded into corporate culture, like your service companies like Halliburton and Schlumberger. And there's a lot of know-how and practical case histories and a lot of many hours of experience that they develop. In other words, if you try to frack your first well, you're probably going to screen out, which means you're not going to know when to turn the valve to off, and you're going to fill up your whole wellbore with sand, and then you have like a 2 or 3 day cleanup operation. And if you do this on every well, pretty soon you're an uneconomical operator. So to become a profitable or economic operator takes a lot of experience. And so that's what I'm saying. Technology just isn't on a piece of paper that can be sent on an email to a different country. It requires a lot of expertise and practice. Just like you guys do homework problems to practice so that when you get the test, you do well. Okay. Without a real program lecture here, get caught on a couple of tangents. But now I know where I was. This gas, what is the primary measure of gas as it's going down this pipeline? Before we measure the composition to get the heating content, what do I know about that gas? What's the most simple? What?
Fluoride, how much do you have?
Yeah, no, but I'm talking about an intrinsic property of the gas.
Mass flow.
I may have heard it.
Mass
Pressure,
flow.
line pressure.
Volume, temperature.
Density.
Composition?
Density or
BTU.
gravity. Okay, so the gas gravity is the density divided by the density of air, or the molecular weight of the gas divided by the molecular weight of the air. Okay, so most of the gas gravity in our U.S. pipeline system is a gas gravity about 0.55. And there is more than one compositional blend that would make up a specific gas gravity, but they tend to have the same ratio of C1 to C2, C2 to C3, C3 to C4, because they're all kind of have, it's like saying most human beings are between 3 foot and 6 foot tall. There's some similarities between the gas properties. So gas gravity is probably the primary measure. And we're going to be using some software tonight that will tell us that we can get many of the properties that we need with just this. So usually the properties that we need at temperature, and I never put it up here, my phase envelope. We need temperature, pressure, and gas gravity. And then we're going to add, because of the software that I'm going to give you, and I'm just going to tell you right now, we usually tell it how much we have in impurities. This is a very minor effect. We could put 0, 0, 0 for in many cases. By and large, the properties that we're looking for the natural gas is a function of its gas gravity, and then at what temperature and at what pressure. Now, I'm going to get back to this. One of the major things we're going to look at in chapter 1, so you can read this, and this is what I would like you to write down that I want you to know before next Wednesday. This gas right here sells, and it has a gas gravity, and I think the textbook calls this 1. Because the idea that we could have 2-stage or 3-stage separation. Okay, so let me give you an example. Let's say our liquid comes out, and it usually goes to something called a stock tank. And that stock tank holds that oil in it, and it gets, on a warm day, what's going to happen to that oil in that stock tank?
It will shrink.
Huh?
If the temperature is higher, the volume will shrink because the gas will come out of the.
The gases come out.
Yeah.
So there usually is a vent cap, okay? And if you ever just drive by an Oklahoma stock tank, you can actually see the heat and steam come out of that vent, okay? And if you just have, this would just be called 2-stage separation because you just have
HQ
this.
and low peak.
Yeah, so that would have a gas gravity, but if this is approximately 0.6, this might be approximately 0.9 because it's coming up the very heavy ends. And by and large, this is wasted, okay? So you'll hear the term recovery systems. And so what most operators do now is they capture that gas that comes off the stock tank, compress it to a higher pressure, and try to feed it back in there. And they recover that gas that's usually vented out the stock tank. Now, the other thing is we're just talking about this one case right here. This is the one big thing I want you to get out of chapter 1. What's the gas gravity in the reservoir? Was the gas, if this is, even if this is 0, we're in Alaska, so it never heats up, okay? It might freeze. Even if there's not leaking any gas gravity from the stock tank at all, what is the gas gravity in the reservoir?
0.6.
It's 0.
Be higher than 0.6.
It would be higher than 0.6, and why?
It's all your liquids.
All your liquids were very heavy hydrocarbon chains. And when you add those heavy hydrocarbon chains in with those methane and propane molecules, it's a much heavier gas. So what is the primary thing that we would measure at the surface that would give us a clue to how much heavier that gas was?
Yield or the GOR?
The yield, or the GOR. So the yield is usually in MCF. And I'm fairly lazy. Most people would say MMSCF for 1,000 cubic or million cubic feet at standard conditions. And most units are designed so the number's between 1 and 100. MMCF per stock tank barrels. And typical yields are 50. 50, no, I'm sorry, I got this backwards. Eraser. Am I looking at one? Yes. Yields are in stock tank barrels per MMCF. And typically they're 50. They could be 100. They could be 150. And the higher that yield is, the more liquid that comes out of the ground at the same time the gas is. Once we put it back in, the higher or more we have to raise the 0.6 number. Okay? Now, the reciprocal of yield is GOR. And it has units of standard cubic feet per stock tank barrel. And it's usually on a range of 8,000 or 9,000 or something like that. But again, we drop the off so that we can get whole numbers. Because if you reciprocated one of the other numbers, you get .01, and then engineers like numbers like 10 and 100 and 200 and 300. They don't even mind 8,000, but they don't like to deal with .01. So they're equivalent measures, GOR, but typically, since this is a gas course rather than an oil course, you know, I come from being a reservoir engineer and working both oil and gas, and so I used to put everything in terms of GOR. But this is a natural gas engineering course, so yield would be the preferred number. Now, if the yield is 0,
There you go.
then this number equals this number. Because we're not adding any heavy ends, larger amount of hydrocarbon chains into the stream. Okay, so when we do reservoir engineering, we have to know the gas gravity in the reservoir. Because if I'm trying to determine the gas in place, I use a number called a formation volume factor, which is the amount of reservoir cubic feet in the ground is occupied by the number of standard cubic feet at the surface. I will just refer to it as B sub G, the reservoir formation volume factor. This is all in your textbook. And the only thing that you'll see in there suspiciously is a little character called Z, which some people call the compressibility factor, some people call the supercompressibility factor. And Z is a function primarily of gas gravity, reservoir temperature and pressure. Remember, I'm on a pressure scale and a temperature scale. So if I want to get some kind of property, I would have to know its gas gravity. And I need to know its gas gravity in the reservoir. So one of the things that I'm going to expect you to be able to do is be told, I left a couple things off here, this oil also sells, and its measurement is of density, but it has a really funny scale. Does anybody know what that is? API, okay? And it's counterintuitive, the API scale is, the higher the API,
High quality.
the higher quality, but it's a lighter,
Light, yeah.
less dense oil. The lower in the scale is such that if you get an API of 10, it has the same density as water. But what you want to be able to do is, given a yield, or depending upon the equation, may call for a GOR. If you had the yield, you had the GOR. If you had the GOR, you had the yield. And if you're given actual production rates, you can calculate it. It's just one divided by the other. Given the yield, given the API, given the separator gas gravity, I need to know what the reservoir gas gravity is, okay? This is not an unreasonable request. And it's very important that we know this. Because this is not a midstream class. Okay, this is a reservoir class. Look through this book, okay? So it's very important that I can take surface conditions, typically things that are measured, and be able to interrelate them into things that I need to know. Okay, I'm going to erase the board. Let's do, okay. Who can tell me what the ideal gas law is? PV equals NRT. Who can tell me what the non-ideal gas law is?
PE5613.
Equals Z NRT. I'll write that down. Okay. that's not new to anybody, is it? In fact, you knew that before you went to college, or probably were exposed to it in high school chemistry. Okay, so you should be able to work problem. We're going to do this in class right now. That's why I had you pair up with somebody with a computer. We're going to work. This is my favorite problem. We're going to work problem 1.3. So this is a laboratory experiment. A cylinder is fitted with a leak-proof piston. Does everybody know what a piston is?
What page are you on?
I'm on page 33. Does everybody know what a piston is? The volume within the cylinder can be read from the scale for any position of the piston. The cylinder is immersed in a constant temperature bath maintained at 160 degrees, which is the reservoir temperature for the gas that it came from of interest.
Did you skip to Fahrenheit?
What?
160 Fahrenheit? or-
Yes.
I think so.
And if we were going to, what units do we want to use here? Radian. And how do we get from Fahrenheit to radian?
At 460.
Add 460. Pressure's already, doesn't require any adjustment. About 45,000 cubic centimeters of the gas measured at 14.7 and 60 degrees. What do we call that?
Or atmospheric conditions.
Yeah. Atmospheric conditions.
STV.
Who can tell me what Z is at atmospheric conditions? 1. And some people will argue, is this 14.7, this is 14.696, this is 14.73. It's so close to 1, it doesn't matter what those things are. Okay. Z is 1 at atmospheric conditions. I'm defining that for this problem. Okay, the volume is decreased, the piston's closing, so the volume, okay, so they have a volume of 45,000 cubic feet, or cubic centimeters at atmospheric conditions, and then the first thing they do is they calculate the volume of that at 300 psi and 160 degrees, and then all these volume pressure measurements are at 160 degrees. Calculate and place in tabular form the Z factors. Okay? You have a constant temperature situation. You basically know Z and R
1.7.
from the initial conditions, because you know that at 60 degrees, 14.7, and this volume, right? You're given that. So you basically know, and Z is 1, so you know NR. You don't care what N is, and although I know R is 10.732 because I got it memorized, you don't need to know that. All you really need to know is what NR is. Okay, does NR change? No. So at those other pressures and volumes, and you do have to make a temperature change, but the temperature change does not affect NR, doesn't affect N, the number of moles of gas. You should be able to calculate and see it for those other values. So let's go ahead and open up the spreadsheet and calculate Z's. I'm going to plug it up. Equipment.
I think I have all the information. What was the pressure inside the
45,000 cubic.
volume was 45,000? And the pressure was 300?
What was
Inside.
45,000 at atmospheric conditions?
Oh, it was 45,000 at atmospheric.
Yeah, so then you
Okay.
have to calculate the volume at
And the temperature was,
520.
okay, and that's one. So R equals P over T. I'm not used to using all English units. Do I need to convert anything? It's so much easier using metric.
This volume for that should, I believe it's cubic centimeters.
Oh well, it'll be proportional, so it'll be proportional to that. Okay, and then inside 300. Okay, and that's going to be constant. And it was 160. Okay. And the volume.
This is all I wrote down.
Huh?
This is all I got.
He didn't give us the volume for inside.
Do you have the book?
Nope. Too many unknowns. Did you say what the compressed volume was?
Did I say what?
What the compressed volume was, or what the compression ratio was, or?
The table just tells me that my first pressure is 300 pounds. And then it tells me the volume is 2,529 cubic centimeters. You guys don't have the table?
No, we don't have a book.
I'll write these numbers down.
Thank you, sir.
That's what we're missing.
Like, I don't tend to be an expert at math, but I got too many unknowns.
Of course, what you want to do is calculate Z.
Correct. Oh, there's multiple volumes.
So that pressure heat up, it's PSIA or PSIG? Thanks, sir.
Oh, wow, okay.
And drag it across.
Yeah, yeah.
The volume facility is cute.
So I've got 750 and then 1500.
Yeah. It's a simple, you know, it could be in meters cubed for all you care, as long as you got the fact that it's the same units as the 45,000.
Oh, and it's constant temperature.
Yeah.
Looks like
You're only going to end up ratioing those numbers.
620.
Okay, I'm going to try to use some software.
It doesn't seem right.
Well, click on this real quick.
Did I get? Can you see that better than I can? 142. That makes sense.
So they go down, then they go up.
Hmm?
So they go down, then they go up. Do you want the 20, is the back to ideal only?
Restricted. Just rank.
defined. Who's got a Z for 300 pounds?
0.962?
0.962. Anybody get a different number? You guys are good. Who got a number for 6,000 pounds? What?
1.081.
1.08 what?
2.
Okay. How about if I call it 1.8? Okay. If you get the first and last number, you can get them all. Okay, now, go to D2L and download a spreadsheet that I just put up there called software.
What is it called?
Should only have,
Is it the gas PVT?
yeah,
Okay.
and I should have had you
Some
do this
macros
first,
here.
but copy paste your calculations from your original from your original spreadsheet into this, to sheet 1 on this spreadsheet. It's like this. Go to the spreadsheet you already wrote that has your numbers, do a Control A, and then a Control C. And then go to that new spreadsheet and do a Control V. Okay? So now you should have 2 spreadsheets with the exact same looking calculation. All right? Delete the first one and just have the one that has the, or I mean, close it. I don't mean delete it. Close it. So you only got one spreadsheet open.
Nothing inside.
Now, you add the cells 160 and add a cell that says 0.5. The 160 is, of course, representative of the reservoir temperature increase variance. Okay, now you have a table there, right? Now you have calculated Z's, right? I call them lab calculated Z's, okay? Now let's calculate Z's with software. Okay? So let's go to that first cell where you don't have anything yet, right? And hit the f of x on your formula bar.
Go to what cell? First
Well,
cell for Z
right
software?
next to 0.962.
Okay.
Okay, hit f of x. You got a dialog box?
Mm-hmm.
Go to the bottom where it says user defined.
What is the name of the
Z.
Okay.
You can actually just put equals Z. Okay, and then it should prompt you for some things, right?
Pressure,
What does it prompt you for?
pressure, temperature.
Okay, for that first cell, the pressure's 300 pounds, right?
Mhm.
And that was a prompt for.
Temperature,
Temperature's 160, you already got that in the cell, right? Then what?
G.
That's 0.5, that's our initial guess,
Oh, okay.
okay? And then it prompts you for the impurities, just put 0, 0, 0. How many people have done that?
Okay, equals Z, pressure, temperature, gas 0.5.
Don't enter 0.5, put 5 in a cell. So that
Okay.
when you change
And then lock it.
0.5, okay, I have a problem with students with doing this. Never put numbers, put cells that are being referenced, so that you can change the cells everywhere you change it. Because if I asked you, if you want to try a different number, like 0.6, I don't want you to edit every cell in that column.
So you want us to lock it on that cell?
Yeah, I want you to lock it on a .5 and a .6, yeah. These cells should be F4. $A, $1 if it's in cell A1. Lock in that cell.
What is 6.5 stand for?
It's my guess.
The
We're gonna
gas-
change that.
For Z though?
No, it's my change for, it's my guess for gas gravity.
Okay.
Z needs a gas gravity. What'd you get for Z?
0.9999.
Okay? So that's good. Now copy it down.
Hmm?
And what'd you get for 6,000 pounds?
1.140.
You're not that far off, are you?
No.
Okay, pretty good guess. Now, you two guys circulate and make sure everybody sees what you see.
Oh, man.
Show them how to use the software.
Have you guys done it? Yeah, we're using Visual Basic. The software.
He put in a function, he programmed a function into it.
Yeah.
So go to the spreadsheet that you made.
You don't have what?
Yeah, copy.
Excel.
You don't have Excel? How do you not have Excel? You're not an engineer.
I know, but it's on the computer, so I'm going to get it.
Okay, yeah. See, this is, to find out what our major design problems are.
Would it just be 252?
I assume that if you're an engineer.
Oh, I'm sorry.
Yeah, I
Excel.
don't run my own.
Okay, yeah, you can't do this out without.
I got a different number for NR.
In fact, they made tablets for a long time. And I kept checking tablets. Until they had the all-tablet machine, where I could go into Visual Basic.
I got 1272.
It's good for reading. That's all tablets are good for, until they came out with Surface Pro, which actually has downloadable software.
Yeah, 45,000. PSI is 14.7.
Yeah.
Yeah, I wanted to get.
Temperature is 520.
Yeah.
60 plus 60 is 520, not 620.
No. Check the numbers that you're using. Your formula. Check. Make sure it's using the right numbers. No. Inside the vessel is 620. Inside the vessel is 620. Yeah. The first data one is that standard temperature and pressure, 60 degrees Fahrenheit. But all the ones after that, it's
Do you have
constant
the
160 degrees Fahrenheit.
Go to the Google LSU PBT HP4160.
620.
LSU space PBT space HP41. Yeah.
Yes, and then drag that down.
No?
Okay, now copy all your data.
Oh, this is it.
Select and copy all of your data. No, I mean like the whole sheet. Yeah. And then paste it into that new.
So there should be.
Yes. Okay. Now make yourself a new column here. Call it Z software. Z software.
And
Yeah.
R for the regular one?
Okay. Now he is programmed in a function. So what we do, now this is just to kind of show you where it is. So we go here. We go to category user defined. This is it. You see, there's one Z documented G. The variables are pressure, temperature, and G is the initial gas, because it's like the iterative T. And then composition of N2, CO2, H2, sulfide. So he said just use the 0.5 as an initial gas. Leave that in. Okay. So that's why he was saying. Oh yeah, you get constants over here. Okay.
Maybe this is a better way to teach. I no longer have to prepare. I just wing it every time.
Let's do.
Explain quickly, like what's, I don't know if I should know this well, I'm not drilling, but what's horizontal drilling and
Okay.
fracking?
Yeah. Well,
Well, this one's
Google
520.
hydraulic fracturing, and then go to images.
Pressure, temperature, initial gas. 000. There you go. So, which will make you go into that and lock those variables. Yeah.
You guys don't really need teachers anymore. Everything's running here. Here it is all, everything I'm talking about right here. Okay, so here's my drilling well. And then I come in and you see my, we never used to be able to do this. We go down, we turn the corner. And we drill horizontally. Now, we used to be, we only could drill this way for 100 years. And so we can only expose ourselves to this much of the formation. So now, the formations we're producing are about as porous as this porous. But by drilling a horizontal well, these are 1 mile to 2 miles horizontal. And then we inject.
Did anybody else need help? Yes or no?
Oh, fine. Making fun of me. Then we, I'm trying to get a surface picture of a bunch of trucks. You can see all these trucks and stuff like this on their. So all this stuff is pumped into the rock and it breaks it up. And what we're trying to do with the horizontal drilling and the multi-frac is increase the surface area of the formation to that drawdown, that wellbore drawdown. And we do it by almost $1 billion full.
Wow.
So we used to produce wells that had Darcy permeability. And we could produce wells that had millidarcy permeability. But shales have nano Darcy permeability. There's actually a ratio of 1 billion to them, the ability of that rock to conduct fluid through it.
Okay.
So we've made up for that by increasing the area 1 billion fold.
Gotcha.
Okay? So with technology, we've always known that shales contain oil and gas. We just never could get it out.
So with this technology?
With this technology, we get it out. No problem. Okay. Now, you guys are all good at Excel, right? You should be able to highlight the pressure, the laboratory calculated Z's, and the software calculated Z's and insert a scatter graph. Right? Huh? You all got that done? In other words, the way you were doing this, if this was test problem is you have your Z data. I think it goes down, then goes back up, right? Okay? And if it's data, it's a symbol. If it's a numerical or analytic expression or a computer simulation, it's a line. Okay? So have your calc Z's as a line and your lab computed Z's as symbols. Okay? And then the next thing I want you to do is play with that 0.5 and see if you can't tweak it just a little bit better so that the line fits all the data. Huh? Yes, go join some other groups. I'm so glad that you actually took the initiative, you know. So you can just slide over here and you can come down here. Z. That's really hard font. Okay, we're graphing.
Graphing.
Yeah.
As a function of.
Put the real gas law computed Z's as symbols, and then software computed Z's as a line.
What's the x-axis?
So if you highlight these three things right here, it should automatically give you this on the x-axis, and these as two, series 1 and series 2. Depending on your version of Excel.
What do we both see? The actual and actual and calculated.
What you do?
Series A. Z lab. X value. You want us to just do linear? Just a linear graph?
No.
I mean,
Highlight this,
mhm.
and insert a scatter graph. It should give you pressure on the x-axis. This is series 1 and this is series 2.
No, I'm asking, like, you just want a linear function of pressure, not like a log function or.
Oh, yeah, Cartesian. Is that what you asked me?
No,
Did you use the word Cartesian?
no.
What'd you use?
Log? Because it,
I think.
because it goes from
Oh,
such
you
a.
said linear though.
Yeah.
Yeah, if you would have said Cartesian, I would have understood.
Oh, okay, sorry.
Because when you said linear, I thought you were talking like a line graph rather than a scatter graph. Okay, now, can you change 0.5 just a little bit and get a better fit of the data?
What on earth is going on here? Hello. See, that's the software.
Can you get that line to go through that, all that data a little bit better by varying 0.5?
Yeah.
Okay, you got a number?
Why is it reading like that?
0.65.
0.65. Anybody else get a number?
Just one. It's 1.6.
It's what?
1.6.
1.6? Okay, click on your Z. Just click on one of them. Click on your formula.
Not using this.
Yeah.
Yeah, I just put it up there because you did.
Okay. There's a little bit of a problem here is that the ideal gas law has to use degrees Rankine, right? This Visual Basic function is for engineers.
So she's in Fahrenheit.
Okay.
It wants in degrees Fahrenheit.
160.
So you need to have
Yeah, close.
you need to have 460. But put it in a different cell. Just don't change that because that'll change your other word.
So you just have to put 100.
I mean,
Let's see.
160.
Temperature is
And is it? Yeah.
P4. Oops. Close that.
Just do it in one and then copy.
He said it was supposed to be
You do it every
linear or logarithm. What did he tell you it's supposed to be linear or logarithm?
Just disregard that question. I was asking him how he wanted me to graph it, and
Oh, I was asking
Didn't matter.
about fitting. Because
Now,
fitting.
change your point.
oh, you play around with the guessed value to try and fit the curve as best as you can.
Are we fitting it to calculate that?
The lab data,
So we've just managed to marry, two sciences: chemistry, degrees Rankine, and engineering, degrees Fahrenheit. See? Okay, did you guys come up with a similar number? Okay. Did you guys up here get 0.65? Is it better fit? Okay. Okay. Now, let's pretend we didn't have that graph. Let's do the same problem again, come up with a number like 0.65, but do it behind the curve. Okay. So we'll add a column. We'll call it air. Okay. So typically the air is a relative air. So it's this minus this divided by that. And when we're checking a lot of airs, we could have a lot of fluctuation if some are positive or some are negative. So we try to make the relative error of the same magnitude. Some people use the absolute value of that mathematical expression. Let's square it, because that's what you normally do in a least square fit on a linear regression analysis. So remember, this is the true answer. So you want the relative answer to the true answer. So take this number and in parentheses subtract that number and then divide it by the true answer. Take that whole quantity and square it. Okay?
Okay. Which did you want us to use as the denominator?
The true answer, because you want a relative. You want a relative answer.
The lab being the true
True
answer?
minus calculated
Uh-huh.
divided by true. So you'll need at least one set of
I guess I didn't-
parentheses.
Oh,
Then you add a
No, he wanted us to
parentheses around everything and square it. And that otherwise you'll have some negative errors and some positive errors, and you
Well,
may have a bad answer, but it
yeah, I
may
was
look good.
getting
It may
ahead of
look
him.
like you have zero error.
that's a pretty small number.
Yeah, they're going to be small errors. But then, hit your auto sum button and give me a summation of the error down here. Well, okay.
That's a
But
percent?
You've already,
Wait, no. 'Cause it's-
you've already peeked around the curtain and got the right answer. Okay.
We'll start back at 0.05?
No, we're not done yet. We're not done yet. Now, how many people have used Solver before? Have you got Solver loaded? Okay, so what you want to do with Solver is you want to set this to a what? Minimum.
Mm-hmm.
Goal seek could let you solve for a true solution where you had the intersection of a line going through the thing. But you probably can't get zero error. And so goal seek may not work, but solver will if you set that to be a minimum. Okay? Because we've squared it, so it's going to be a positive value. The best we can do is make it as small as possible. So solver does that. Now, you may have to go to your main menu and add solver into your tool pack. How many people have ever done that in their life? Okay. So we've got 4 hands. If you don't know how to add solver, ask one of the people that just raised their hand, and they'll help you. You guys got solver? Okay, there you go. He wants it.
Do you know how it is?
She'll help you.
What do I know? You just want to add it?
Just listen to
Add
this.
something.
How do you make it
Anybody else
active?
need solver? Okay, have you guys got solver? Any needs help?
I think that's it. How do you make the add-in active? Manage.
Excel option.
There we go. Okay. Solver. And we're going to.
It's okay, but
Let's do it here.
you might have to.
No. No help available. Excellent. Solver get. No.
What we want to do. Solver.
I'm hoping it'll walk me through it going. Okay, what are the variables?
What values are, what's the variable cell?
The variable cell is your gas gravity. That's the only thing you can change. You want to change gas gravity so that this is a minimum. Well, maybe your variable cell is your minimum. But then by changing this, I forget how the dialogue.
I think it's the objective is to change.
Yeah, your objective is this to be a minimum. By changing your gas gravity.
Minimum is 0. What's our minimum objective?
Minimum. Did you get a number?
We're loading solver.
So you're going to set your target cell to be, is this
Okay, and the set objective.
Okay, so set that one. And you're going to do the minimum.
On the data tab in analysis group, click solver.
What we have first is 0.5. 0.658.
No.
It's point what?
658. 659. And then normally you would set constraints if it's really specific, it's 0.0, blah, blah, blah. So hit solve.
Now, if you're bored and ready to move ahead, I'll tell you the next thing. Now that you've got that, I want you to tell me what
Okay,
the
data.
viscosity is and what the compressibility is.
Now we're talking. Set objective. Minimize.
And if you go hit Alt F11, you'll find out what the names of those functions
You
are.
already have the right answers, so like if you put like an 8 or like you
Subject to the
so
constraints.
try that.
We got .653.
Okay, now change that to like 0.8, but there's something wrong. So close to your gas tank. So you don't.
That's my only variable.
Still. Yeah, close it. Yeah.
Subject to the constraints that it's going to be less than
That's right.
1.
And see, now I can calculate that. You're welcome.
6586. Nice.
Can you remove the time real quick? What you did?
Yeah. Did you see how I added in the solver?
Yeah, I got that.
Okay, so then I went to the data tab, and over here in analysis went to solver. And I set objective, which was the error. That's where the goal is, and we're minimizing it by changing
Oh, did you hear the next
this
step?
variable
No,
cell,
sorry.
which
I know you were
is the
busy
gas
working.
gravity, I guess.
I want two
And
more
then I
columns.
just put in some
Okay.
constraints
The gas viscosity
Okay.
and the gas
that it could only vary
compressibility.
between 0 and 1.
Those functions are in software, and to figure out what their names are, you can do a trial and error, or you could just go hit F11.
Yeah, that's exactly what I was hoping for. It's very straightforward.
Well, look on that.
Oh.
Sorry, Dr. Keller.
Okay, do it this way. Hit the function key. You should get a dialog box. If you scroll to the bottom, it says user defined.
What'd you want us to do?
I want you to calculate that. I want you to calculate the gas viscosity and the gas compressibility at those pressures in 160 degrees Fahrenheit using the software.
I'll say that one.
Oh, using the functions. Okay.
I feel like I don't know those formulas.
My user function.
Here, let me get my glasses and come on.
Oh, there we go.
Wait, we've already done the compressibility, right?
That comes second.
Name off the functions. You see Z?
A different compressibility?
Now guess which one that is?
Compressibility factor.
CG.
That's
Yeah,
compressibility of gas. You're gonna use that one.
Okay.
That's
Now you
confusing.
see an
Yeah, I
M.
have another professor that calls
Okay,
it.
that M is.
Wait, I see it in.
This is compressibility,
Yeah, no, it's not the
period.
M, that's pseudo pressure. M-G. We're using M for mu. The normal viscosity symbol is mu, which sounds
I see
like.
a UG.
Oh yeah, UG, that's it.
Okay.
UG,
Okay.
which looks like.
UG?
Okay.
I knew it was in there somewhere.
So it's the same values.
Calculate UG and CG at 160 and those pressures.
And we're not doing calculated on, it's only the estimated based on the worksheet, right?
Here, whatever you get for a final gas gravity. So basically,
Wait,
you
this is
solve
wrong.
for gas
This is
gravity,
wrong.
see that? Now you're gonna use that gas gravity to get other things. You match Z, now you know what your fluid is, so you can calculate viscosity and compressibility.
This is gonna bug me, so I'm gonna do this.
Your spreadsheet.
Yeah, this is
And
gonna
it's
make me
still
feel a
gonna
lot
be at
better.
the same PT variable.
Yeah, at 160 degrees and those pressures. So lock in yourself for 160 degrees Fahrenheit, absolutely, and let your pressure vary.
And this should stay the same. Yeah, okay. You're getting a glimpse of my OCD.
Like most engineers are.
Okay. Ugh of pressure, temperature in Fahrenheit, and then this, and 0, 0, 0.
You can always jump on with somebody else too.
Well, I know what you're doing, it's probably like that, where you through the solver.
I assume you're following everything I'm doing.
Yeah.
Okay.
Yeah, I had
Now,
a
what's the
TA
units on that viscosity?
Is that in centipoise?
All this Excel spreadsheet were in Spanish.
Is that in centipoise?
I know what you're talking about.
Darker colored?
Yeah,
Is that gonna be in centipoise?
yes.
Yes. For the
Okay, the
viscosity?
documentation for the software, you can, if you want it, you can get it by Googling Louisiana State University. This used to be, when I was a practicing engineer, we used to have it on our calculators, which were HB 41s. So LSU HB 41 and then PDT back. And they'll give you the entire documentation.
Thank you.
Yeah, one of the first things I did is download this when it came here.
Nice.
Once I found out about Visual Basic, I go, I wonder if what I used to be able to do all the time is available here. Sure enough, some
And what's the units
professor
for
at LSU
compressibility?
converted everything we used to have, which was written in assembly,
Yeah.
to Visual Basic.
Nice.
Did you just want us to find those, or do you want us to graph them and?
No, you don't have to graph them.
One
Then we're gonna do one other thing after that. So then the other one is M of P.
PSI.
Then we'll talk about that, then we'll call it quits. M of P, also shown as P sub P for pseudo pressure. And then in BB here is just going to be, I think, MP. But like all those other ones, it's just a function of pressure, temperature, and impurity. And gas gravity.
The function is not working with us.
How realistic is that statement of 000 for all those impurities?
Oh, well, we don't know anything about saving gas.
Well, I just mean like in reality, how.
Oh, it's not going to affect it that much. I mean,
Okay.
you know, obviously, the greater the impurities that may be in the saving gas, like 20% CO2, then we'd be off.
Yeah.
But remember, even with our very first gas at 0.5, it wasn't hugely off.
PSI minus 1.
Now, if we were given something like Z and viscosity, we could actually tweak the impurities so that it matched both the pressure-volume relationship and the viscosity relationship. We don't have any data in our textbook to do that, but I mean, theoretically you could. Typically, okay, on a typical gas analysis that we get from that third-party sales midstream operator, it'll tell us what our impurities is. Stuff we know. In a typical situation, we know what those are. In this textbook example problem, we don't, but it's something we normally know. Okay, so I've asked you to calculate gas viscosity, gas compressibility, and pseudo pressure, which is MP.
MP.
They're going to be big numbers, so what I normally do is just show them in scientific notation. You got M and P?
I did not get the viscosity.
Okay, they're VV functions.
Is that PSI?
Well, yeah, just hit F of X.
It's asking, it's showing a value there for usually in TT.
Did I use the right temperature last time?
This is a pressure.
I'm gonna find out. Yes, I did.
Just, you don't do this, just let me look at them all. Scroll down. Scroll down. You didn't give it an H2S yet. Okay. Okay, I was gonna send you back to kindergarten.
Did you say yes, that's in PSI?
Okay, so I'm going to end this in just a few minutes. As soon as everybody's got pseudopressure, I'm going to talk about what pseudopressure is. Okay, this is my fluid flow section of the course. Darcy was a groundwater hydrologist. You know, he looked at streams that went in underground. You know, the Canadian River that runs right out in front of us? You know, a lot of times you see just sand out there, but it's still flowing, it's just underground. Okay, so groundwater hydrologists, they think that's fascinating stuff. That's not a lot of money. So he just made himself a course lead, filled it up, you know, and then the first thing he discovered is that, you know, if you hook this up to an apparatus that you could have a higher fluid level, greater delta P, this is atmosphere, he found that flow rate was proportional to the pressure drop across the court. Okay, then as petroleum engineers, we came in and we decided that this is good, and then the constant that he had in there was the permeability, which was a Darcy. And you can see the permeability was really high because this is diatomaceous earth, you know, it's sandbags, loose sandbags is what it was. So that's why when we talk about Darcy permeability, that's huge for petroleum reservoirs. Typically a good reservoir is like 100 millidarcies. Then petroleum engineers, we don't just deal with water, so that would have a viscosity of 1 because it was atmospheric conditions and it was water. So we would have a viscosity term in there. Now, for both water and for oil, viscosity doesn't usually change too much. But for gas viscosity, as you saw when you tabulated this data, you have what, maybe a factor of 2 between your highest and your lowest? So we can't consider that a constant. It changes. So what we're interested in flow rate, and we're interested in what drives flow rate. And for gas, I'll always use lowercase q for flow rate. Flow rate of gas is proportional to pseudopressure. Historically, it was called M of P, and that's why your VV function is MP. Okay? So we want to use M of P in chapter 1, but I'm just showing you that it's another one of those things. It's just a function of temperature, pressure, gas, gravity, and impurities. And all through chapter 6 and chapter 9, when we're talking about dynamics, not just static conditions, we're going to be using pseudopressure all the time. And it's on the order of pressure squared divided by viscosity, which is a number less than 1. That's why it's such a large number.
So PP is pseudo pressure?
Yeah, P sub P is the current SPE nomenclature for pseudopressure.
Okay.
And so oftentimes you'll see equations like pseudopressure average minus pseudopressure of the well flowing. That's the way I would write that.
What is it?
Remember that first slide where there was those P average, PWF, and P external?
Yes. Mm-hmm.
When in gas engineering, it's not the pressure, but the pseudopressure difference that is the driving force for flow. So we got to get, for liquid, and originally when this was for groundwater hydrologists, for water, which is even the simplest case, pressure is the driving force. but for gas, it's pseudopressure. So we gotta convert all of our pressures at some point in time to pseudopressure. And they're big, huge numbers, and they're hard to look at, and they don't make any sense, but you just gotta learn to live with it.
Will you give the equation for MP again? Sales pressure squared over pressure.
Oh, no, it has, that's not the equation, it's an integration.
Oh, okay.
Z over P mu P dt. Where is it in our textbook? It's in our textbook. Let's see how far I was out. Pseudopressure, 174.
Say what?
142.
I have an article that's written by Wattenberger.
Mm-hmm.
That goes over everything it is.
Yeah?
It's really good. And basically, everything we've done, I walked step by step. Show you all the charts.
Here it is, 83, equation 5.4. I got it upside down.
Pages long.
And there's a factor of 2.
Like a journal article? Oh,
It's me.
SP, okay.
Arctic equation 5.40. Pseudopressure as a function of P is 2 times. It says a pressure base, but you can use 0 as long as you're using PSIG. But their definition is at some low base pressure to that pressure. So pseudopressure as a function of pressure, this pressure is the upper limit. So basically, if you plotted pressure over mu z versus pressure, the area under the curve up to that pressure in question is going to be the pseudopressure. So for the rest of chapter 1, you're not going to use it too much, but I just wanted to let you know that I gave you the whole arsenal. In other words, this book was not taught with the idea that you'd have these functions. And so what we'll do is we'll override. And when we get into chapter 6 and chapter 9, we're going to have these long tables of pseudopressure. But we're just going to tap the corner of the box and have it fill in for us. Okay, I think that's a good quitting point. We didn't take a break tonight. I was typically, if we're going to go this long until 8:30, we'll take a little bit of a break. And if you guys just remind me or something like that, sometimes I forget about that. But we can always take a break for either to get something to eat or use the bathroom or whatever. And I don't have any idea what's going on with the equipment. Maybe we have a true distance learner that's something that we're just going to miss the whole lecture. Like I said, what I'd like you to know is read through the portion of chapter 1 where they utilize surface production properties to garner true reservoir fluid properties. Because that's what we have to be able to do to calculate Z, mu, compressibility, formation volume factors, pseudopressure. Okay, hang around here if you have any little questions, but otherwise I'm going to erase the board and you guys are free.